Hi everyone, I hope you're doing great. This is Fuad Moradi and today we're going to talk about my recent PyQt based software designed for wavelet analysis of signals. Today we'll be focusing on detection of optimal mother wavelet for the discrete wavelet transform, and yet the continuous wavelet transform is not in the scope of this project. So when you start the software, this page will pop up, and after hitting the get start, you will have this simple and user-friendly graphical user interface. You can easily load your signal. I will test it first of all on an EEG sample, a short sample of EEG. After hitting the plot signal, you will have the signal plotted in the first tab, in the preview tab. And so first of all, what's the use of applying such a process on the signal? What's the use of selecting optimal wavelet among all possible discrete wavelet transforms? The domain-specific signals rarely fit textbook wavelets, and EEG bursts or multielectrode array, spike trains, or even details of a speech signal have different time frequency fingerprints. And unfortunately, the usual approach that researchers choose to do is to select a bunch of celebrity mother wavelets in the literature, and they start their analysis based on these usual mother wavelets, such as DWT 4 for EEG signal processing, or Simlet 8 for speech signal processing, and so on and so forth. But in this toolbox, you'll have all possible discrete wavelet transform in this list box, and you can choose the header to select all of the sub wavelets, or even uncheck it and select them individually. Okay. What we're going to do is to test the DWT and bi-orthogonal wavelet for this EEG signal. Don't forget to hit import selected wavelet, and then you'll see 53 wavelets were imported. By hitting this find optimal wavelet button, the process starts, and you will have this bar graph representing the similarity of the signal and the selected wavelets over here. You can see that the bi-orthogonal 2.6 is the optimal one based on the zero norm cross correlation metric. Selecting these at the list box makes them red on the bar graph, so that you can easily read the name of them, and you have the number of similarity, the score that you have choose to be applied based on these four metrics: the raw metric, cosine metric, and normalized and zero norm cross correlation. But let's dive into more details. Suppose that you have much longer signals, such as a multi-electrode array proposed by AXION company. Plotting this, you will see that you have almost 800,000 samples in this signal. And suppose that we are going to choose all possible wavelets, and don't forget to select import selected wavelets. 106 wavelets were chosen, and let's do the analysis not in the frequency domain, and choose the time domain for the cross correlation of the wavelet and the imported signal. You will see that relatively it takes much more time to apply this operation, and the step of moving the wavelet on the signal is only one sample. It moves smoothly on the signal and calculates the cross correlation. And finally, the metric or the score that we label to the signal is based on ZNCC. We'll also talk about the ZNCC and other metrics in detail. But there are various approaches to calculate the similarity of your signal and the mother wavelet. The first one is to utilize discrete time warping to enlarge the small wavelet window and make it as large as the 1 million sample signal, and then calculate the cross correlation of these two signals with identical length once, which is not a good approach because the wavelet is gonna be convolved on short windows of the signal. So it is better to calculate the cross correlation of the signal also in the small windows, and that's the reason we move the signal smoothly. We move the wavelet smoothly on the signal and calculate the cross correlation in this way. But a more wise approach, a better approach that accelerates the speed of cross correlation calculation in contrast to this time consuming cross correlation calculation in time domain, is to transfer both wavelet window and the signal window into the frequency domain. So first of all, we will transfer the MEA signal into the signal window into the time domain by taking the FFT, and also if we first reverse the wavelet window and then take the FFT, the fast Fourier transform, then we do the pointwise, the element-wise operation to multiply these two signals, and then take the inverse Fourier transform to have the cross correlation in time domain. And finally, we choose ZNCC, raw metrics, NCC, or the cosine metric to calculate the score of similarity, which differs for different types of signals. The only important point that you have to notice is that you are doing the wavelet analysis in time domain by convolving the wavelet on the signal. But for the detection of optimal wavelet, we are doing the cross correlation. So, and the convolution and correlation have only a difference in the one of the signals that is reversed. So first of all, you have to reverse one of them and then take the fast Fourier transform and multiply them in the frequency domain. And that's all. And you will see after we finish this progress that checking this checkbox, use FFT for acceleration, speeds up the process significantly in terms of time complexity. And the time complexity of the find optimal wavelet currently is O of n multiplied by L, O of NL. And the N and L, O of NL per wavelet operation. So considering that the points of the signal is N and the points of the wavelet is L, for instance, if your signal has 10 to the power of 5 points and the wavelet has 100 points, you have O of 10 to the power of 7. And by taking the STFT, the time complexity, taking the FFT, the time complexity becomes O of n plus n multiplied by log of n plus L. And N and L again are the points of wavelet transform, and the signal which reduces the time complexity significantly. And you will see that the larger the mat file or the signal is, the better optimization in the time you will have. It took a pretty large time to calculate this, and let's simply talk about the metrics also until this operation will be finished. Well, in the metric combo box you will have 4 options. The first one is raw metric, which calculates the raw correlation based on the cross correlation output that you derive from the time domain or the frequency domain. It doesn't manipulate the power of signal or the baseline of the signal. And the drawback is that wavelets with higher energy will have higher score in this comparison. So it won't be a fair labeling, and we are not interested in such a metric for the biosignal processing, especially for EEG, ECG, or even MEA. And the next metric is the cosine metric. And in the cosine metric, the energy will be normalized, but the baseline won't change. The drifts won't change, because in some sort of signals like speech signal processing, the emotions or for the detection of some words, the signal has meaningful DC values, and we are not interested in removing those DC values. But the energy will be normalized, so the sigma won't have much effect on the signal. But the next metric is NCC, in which, in contrast to the cosine, the baseline is removed, the drifts are eliminated, but the energy of the signal will not be normalized, and the sigma has an effect on finding the optimal wavelet. And the final option, which is the most suitable one, is the ZNCC over here, in which you eliminate both the effects of sigma and the effects of mu and sigma, which is the most robust one and the best choice for the biosignal processing. You see that over here the reverse bioorthogonal wavelet of 3.9 and 3.7 are the most optimal one. Let's take a look at the signal shape 3.9. Yeah, that's it. If you plot the wavelet, you see, yeah, this is the shape of wavelet 3.9, 3.7. They are the optimal ones. And the Dobshi's 3, for instance. The Dobshi's 3, let's take a look at the Dobshi's 3. Yeah, it has more high frequency activities, more sharpness, and the signal is not much interested in Dobshi's 3. You see that a bunch of usual wavelets in the textbooks have not much similarity to our signal in this data set. For example, the DB4 or DB6, where are they? DB4, they're not even the 50 ones. Yeah, they have a very, very low order. And that's all. So let's activate the acceleration and see how much time does it take. That's it. Less than 10 seconds, probably. And you'll see that result are almost the same. Reverse bi-orthogonal 3.9 and 3.7 were at the top. And again, you have the same ones when you calculate the cross correlation in the frequency domain. And that's all. Let's test the signal on a sound signal, a speech signal. This is a speech signal. And let's find the optimal ones. Let's see, the Simlet 17, yeah. The Simlet 17 and the Simlet 18 are the optimal ones for the speech signal. That's all. So first of all, you have to load your .mat signal, then plot it to make sure that it is loaded properly. Select your wavelet and plot them if needed. Sometimes you can intuitively guess which wavelet shape and then matches the shape of the signal, and therefore you'll have a better and fair comparison. Then choose the ZNCC or any other metric to calculate the similarities. Notice that always activating this checkbox helps you to reduce the time complexity. And that's all. Thanks for watching.